Going to introduce just two oxidizing agents in this section, PCC and chromic acid, okay? Going to, potassium permanganate is introduced. It does, for our cases, the same thing as chromic acid, but it's not as selective. So know that KMNO4 is going to perform the same thing as chromic acid for now. But if we have to choose one, like ourselves, choose chromic acid because it's much more selective. There's a chance that potassium permanganate can react with more things that are undesirable. Oxidizing agents, we're going to make more bonds to heteroatoms, fewer bonds to hydrogen. So notice that we are increasing the number of bonds to oxygen in all of these cases. PCC is going to oxidize a primary alcohol into an aldehyde and a secondary alcohol into a ketone. Our stronger oxidizing agent, chromic acid, will oxidize a primary alcohol all the way to a carboxylic acid, so a step further than the aldehyde. But like PCC, chromic acid will also oxidize a secondary alcohol into a ketone. There's nothing else we can do with the secondary alcohol. It's as far as we can go. So chromic acid is a little bit stronger. Potassium permanganate will do the same thing as chromic acid, but there's more chance that it will interact with other functional groups that we don't want. So again, know what it does. If it's, given to us on an assessment, you'll be able to know what it does for our case. But if you have to design like a synthesis problem, just use chromic acid. So that's it. Those are the only two we're introduced for now. And the only difference is their primary alcohols. Our weaker PCC can only oxidize it to an aldehyde. Our stronger chromic acid can oxidize a primary alcohol all the way into carboxylic acid. Chromic acid, carboxylic acid. Okay? That's how I would remember it. Chromic acid all the way to carboxylic acid. So similar problems kind of to what was given today in class. We have to design our alcohol, determine our oxidizing agent to get these products over here. So first up, I see that my functional group I have to make is an aldehyde. So to make an aldehyde, I only have one oxidizing agent that can do that, and that's going to be PCC. I know I need a primary alcohol in PCC to make an aldehyde. So my alcohol should have 1, 2, 3, 4 carbons and a primary alcohol. So 1, 2, 3, 4. There's my alcohol, PCC, oxidizing agent. These are going to be very important in synthesis problems. We're going to get a little bit into synthesis in this video, but more like a some common steps in synthesis so you can design your own in practice. Okay, here my functional group, carboxylic acid. I'm fully oxidized, so I need a strong oxidizing agent. I could use either potassium permanganate, but I know that that's more reactive with other functional groups. Even though I'm not given any here, I'm more comfortable using chromic acid. And also this way, I don't have to put, I think I need like OH minus and water or some type of proton source for that, so we can also ignore that. And just write chromic acid up here. 1, 2, 3 carbons. To make a carboxylic acid, I need a primary alcohol with 3 carbons. There we go. Last example here. I have a ketone. I know I need a secondary alcohol, and I'll be able to use either chromic acid or PCC. Either one will work. They both make ketones out of secondary alcohols. So I could use PCC or chromic acid. Either one will work. Okay. Now that's all it's really presented to us. But let's get into some synthesis type. Let's start thinking about synthesis and using these for synthesis. Because now we have a good foundation of reducing agents, and now we're building on oxidizing reagents. So now we should be able to do a lot with synthesis. Add bonds to heteroatoms, take them off, rearrange, attack, elimination, base, acids. We can do a lot of things. I'm going to start out, and I'm actually just this is going to be a step-by-step kind of thing, like a group assignment. It won't be a full synthesis because that would be cruel because there's so many steps here. I would try and pause the video between each step. Think about it. If you don't, it's okay. And then at the end, I would watch it again and be able to predict what reagent is needed. Oops. Okay, so a true synthesis, I would give you a primary alcohol with 2 carbons on it, and I'd want you to make butane out of it. There's so many steps that we could do, and so many different ways we could do it, and that wouldn't be very fair. But instead, we're just going to go step by step, okay? Recognize these, and that way we can choose from these when actually presented a true synthesis example. So one step at a time, one step at a time. I'm going from a primary alcohol, my first step, to carboxylic acid. I'm oxidizing to a full carboxylic acid. What should I use? Chromic acid to make carboxylic acid. I actually use the same example there. So I'll need chromic acid for my first step. Now if I had treated this with PCC, I would make an aldehyde. I need a carboxylic acid, so let me use my stronger oxidizing agent, chromic acid, H2CrO4. Okay, next up, I notice that I eliminate my double bond, so likely something attacked it, and then it's protonated. And what attacked it? I need to add 2 carbons on there. So we need some type of carbon that attacks a double bond. What would that be? We could use a Grignard reagent. So something with 2 carbons on it. MgBr, 2 carbons. And then something to protonate that, right? Because our carbons would attack here. All right. Enolate anion up right there. It's going to attack, push those up. I'll need to protonate that into alcohol, and boom, I added my carbon chain. Sweet. Now we have a Gemini alcohol. So we've actually added our carbons. That's good. Now, next step. I see that I've I realized I should have done another step. Would have been good to know. Remember PBr3. I could have turned one of these into an alkyl halide, or I could just put a bromine there. Just Dr. Andrews uses that one a lot. So anyway, not asked here. I'm changing an alcohol group into a double bond. What are we going to do for that? This one's we've used a lot earlier, first semester, H2SO4. H2SO4 is going to perform, I believe, a condensation reaction and go from an alcohol down to a double bond. What kind of functional group are we given here? What kind of functional group is this? This is our enolate. Remember our keto-enol tautomerization, okay? So I need to recognize that an enolate is OH group right next to a double bond. That's going to tautomerize into a ketone. So is this really a reaction step? Not really. But what might be given is this and that, or we might have to assume that we're going from this. So it is good to draw out. We would tautomerize. And we'll just assume that's intramolecular. If we didn't, we could just put some kind of proton source to initiate that. And lastly, I need to go from a secondary, well, never mind. I just need to go from a ketone all the way down to an alkane. So this would be a reduction reaction. What can I use here? I have a lot of choices I could do. Because I don't have any other functional groups here that could interfere, I could use Wolff-Kishner, I could use Clemenson, or I could use Rainy nickel. I'm just going to use Wolff-Kishner. But because I don't have any other functional groups on there, I could have used the other two just as well. Maybe I used PBr3 over here and there was like a bromine on there. If I have a bromine on there, I'd want to use Clemenson because it's not going to react under acidic conditions, but it will under basic maybe. And you get a double bond in them. Okay, so that's something to worry about, something to think about here. Because I didn't have any functional groups, I can choose any reducing agent I want. But if I had, maybe I have something like this here, okay? My other two wouldn't work, and only Wolff-Kishner would. If this would protonate, and I'd likely add something here under acidic conditions, which my Rainy nickel and Clemenson were. So just something to think about. A lot of different steps we can use, and these oxidizing agent, it's going to be on there. Grignard, likely going to be on there because it's introduced again in this chapter. Good to know because it works with alcohols a lot. Tautomerization in case we get an enol, and reducing agents, which are introduced in this chapter as well. What I would do, and how I did this, I wrote this out and like, okay, what can I do to this? What can I do to this? What can I do to this? And just kept going. I then give that to a student I am studying with, classmate, and then they try their best to do it. They fail, you teach them how, you both learn. I'm going to do one more brief kind of step-by-step synthesis. This one's tough, but it's kind of merging what we learned last chapter with this chapter. So another example here, it's right here. And I need to go to my first step here. What do I notice? Am I being oxidized or reduced? In both cases, I am being oxidized. My secondary alcohol is turning into a ketone, so I could use either one for that, right? PCC or chromic acid. But my primary alcohol is turning into an aldehyde. 5, 6, 7, 2, 3, 4, 5, 6, 7. But my primary alcohol is turning into an aldehyde. Okay, so I would use PCC or chromic acid. I would use PCC, and it should change both of them, right? Secondary ketone, primary aldehyde. I can't use chromic acid because this would turn into carboxylic acid. That would not be good. Does this give flashbacks? It should. From chapter 19. Okay. My next thing I'm given is that magically turns into yeah, turns into that. How do we go from this all the way there? Make a ring. We're making rings. That tells me intramolecular. I'm going to make an enolate. Okay, I need to make a 5-carbon ring. So I need, again, intramolecular, something 5 away. I make an enolate out of an alpha proton. It's just from last chapter, okay? So to get there, I would just really use OH minus. Make an enolate here. 1, 2, 3, 4, 5, membered ring, and we get all the way to there. It looks daunting. How do we go from this all the way to there? But really, PCC, OH minus. Okay? Yeah. So that's like, and what was there before? It was like 6 or 7 different, I think, mechanisms that we should know when presented to synthesis coming up this next chapter. There's a couple examples, I think, in the book that they actually go through, which are nice. And just a reminder, the one I didn't include, turn an alcohol into a very good leaving group, or put a halide on there, PBr3, or PCl3 as well. Put chlorine. All good synthesis steps to know. You can use those, design your own, and practice rather than keep watching me do it.